we don't want to lose sight of what we're doing and what our aim is. So the aim, remember, it's if you have a charge distribution, how do you get the potential? If you know the potential, how do you get the electric field? We're trying to find this new method of getting the electric field in 2 steps. We already said that this is the starting point, the definition. We define the electric field in terms of potential this way, and now we're trying to see how do we get the potential from the charge distribution. I also mentioned that we're going to do this in steps. There are several steps we're going to go through in order to get the final goal of getting the potential from a certain charge distribution. The first step was to get the difference in potential between 2 very close points. The second step, how to get the potential difference between 2 points that are very far. Now, how can we use that difference in potential between 2 points that are arbitrary 2 points, but we're going to do it for a point charge. So we're going to just put one charge in the problem and see if we can get the potential difference between 2 points due to 1 point charge. Because if we know how to do it for 1 point charge, we're going to show that we can do it for any other kind of charge distribution. Because any charge distribution in the end, it can be broken up into point charges. Doing the derivation is different than the way we did before. We already showed that the potential due to a point charge is kq over r. We did it before. But we're going to do it here in a different way. We're going to show how to get the potential difference between 2 points using the integral formula. So let's take a point charge here at this point, Q, and we want to get the potential difference between point 2 and point 1. So we want to get V2 minus V1. And we know that the definition of the potential difference between 2 points, we showed that it's equal to minus integration from 1 to 2 E dot dr. You need to choose a path. You need to make a path going from 1 to 2, and you need to evaluate this integral, and that will give you the difference in potential between 2 points. These 2 points could be any 2 arbitrary points in 3 dimensions. They don't have to be in a plane or anything. They could be any 2 points. I drew here some radial lines going out of the charge just to help us in the solution of the problem. So let's choose, say, this path in orange, and we want to evaluate integration of E dot dr along this path. So to do that, you have to cut up the path into small elements of length. And the nice thing is that we can always change our path or cut up our path into 2 parts. We can always go in a radial direction and then in a perpendicular direction to the radial. So instead of going along this path, this element of vector here, we can go first from here to here in the radial direction and then go in the perpendicular direction to the radial. Instead of going from here to here, we can always go from here to here. We can always write a vector as the sum of these 2 vectors. So the same thing, we do it for all the elements of length. Instead of going from here to here directly, we can always go this path, and this path. Now, since the electric field is pointing always radially outwards from the charge, we know for a point charge the electric field is pointing radially outwards, then the only part that will contribute in the integration is the radial part, because the dot product of electric field and this element of length will give you 0, and this one will give you 0, and this one will give you 0, and this one will give you 0. The only part that will contribute is this radial part. We're going to see, of course, how this works exactly in the derivation, but this is the idea. This is the trick to solve the problem. So we can always cut up, as I said, any element of length on our path. We can always cut it up into 2 parts. We can say it's dr parallel plus dr perpendicular, where dr parallel is in the radial direction, it's in the direction of the electric field or parallel to the electric field, and dr perpendicular is perpendicular to the electric field. So we can always write this dr as dr parallel plus dr perpendicular. If you add this vector plus this vector, it will give you this vector. So now, the electric field dotted into dr parallel, this will have a value. But when you take the electric field dotted into dr perpendicular, what do you get? You get 0, because the angle is 90 degrees between them. So you get only E dotted into dr parallel. So only the radial part, this is why we said only the radial part will contribute to the integration. Now the electric field, what is E dot dr? E dot dr is just E dr. And so you got rid of the dot product because the angle between E and dr is 0. So the dot product is just E times dr times cosine 0, which is 1. Now what is the electric field due to a point charge? What's the electric field over here due to this point charge? That's a distance r parallel away from the point where we want to find the electric field. We want to find the electric field at this point. So what's the electric field at this point? kq over r parallel squared. The distance between the charge and the point squared. So now we converted our integration into a much easier form that we can evaluate. We can very easily evaluate integration of kq over r squared dr. Of course, the kq go outside the integration, and you're then integrating r parallel to the minus 2 dr parallel. The value, I mean, the way we call this variable, it doesn't make a difference. If you call this dr or dr parallel, it doesn't matter. When you're doing the integration, the naming that you use for the variable doesn't make a difference. So this is like doing any kind of integration, regular integration of a variable. So what's the integration of r to the minus 2 dr? It's r to the minus 1 over minus 1. And then you have to substitute the upper limit and the lower limit. So when you substitute the upper limit and the lower limit for r to the minus 1, which is 1 over r parallel, you get 1 over r2 minus 1 over r1. And so that concludes the derivation, that we found that the potential difference between points 2 and 1 is just kq times 1 over r2 minus 1 over r1, or it's kq over r2 minus kq over r1, which is exactly the result we got in the previous derivation we did in the previous videos. And we show here then that the value of the potential difference doesn't depend on the particular path. It only depends on the distance between the charge and point 1, r1, and it depends on the distance between the charge and point 2. That's all. It doesn't give any dependence on the particular path that we've chosen. That means if you try to do the derivation using any other path, you get exactly the same result. So this shows that the difference in potential doesn't depend on the path that you choose.